thank all of you guys for joining us here. I really appreciate you taking time out of your day to talk with us a little bit about the advancements and history of cladding, at least from ARC Specialty's perspective. First off, a lot of people in here know what cladding is, but some of you don't, so I thought I'd start off to say, what is cladding? Well, for us in the oil and gas industry, cladding is or overlay is a process of applying corrosion-resistant alloys to components that will be used in sour oil or gas service. To begin considered sour oil or gas service, you have to have high levels of hydrogen sulfides or H2S. The hydrogen components of the H2S will cause hydrogen-induced cracking in the steel components anytime it comes in contact with the sour product. So to eliminate this risk of hydrogen-induced cracking, corrosion-resistant alloys are welded upon the surface of the steel components that will come in contact with the sour oil or gas. You now have a strength of the steel component and a protective layer of the corrosion-resistant alloy that is metallurgically bonded to the steel. Now we know a little bit about what cladding is. How did ARC Specialties get into the business? It pretty much started back in Dan's day with a simple formula and more importantly, the know-how to implement it. 2 pi r, so 2 times pi times the radius. Pretty much everybody knows that's the formula for circumference of a circle. Well, to maintain travel speed of a weld, especially in the cladding process, is a critical variable. We know that the distance we're welding revolution of the part, which is the circumference, so we calculate the speeds that the table rotates every time that we step in. So the radius gets smaller as we continually step in on a ring groove or the bottom of a bore cavity. Because of that simple formula and a couple of other innovative features, we won the project to develop our very first cladding system. Dan named it the ARC 5i, or sorry, ARC 5i. ARC 1, that's what I named mine. So, so the ARC 1 was pretty much the first system that cladding system that we developed here. It welded vertical bores, horizontal surfaces, integrated with a turntable to rotate the part. The system also included integrated AVC, so that's automatic voltage control, because in the TIG process, the welding voltage is the distance you're away from the part, so it would maintain the distance as it went around the components. It also had welding process overrides. It was real fancy, had thumb wheel switches. And then we also had amp pulsing, and then most importantly, constant surface speed. So as manufacturers, our customers found ways to make the cladding process more productive. It added a few technical challenges to the actual welding process. So in place of machining a bore, and then we would clad the entire bore, and then send it back to the machine shop to have the intersecting bores cut out of it, and then go back to the clad shop so they could weld that area. They decided to do all the machining in one setup. So they machined the bore and the intersecting bores at one time. I forgot to click. And so when they did that, that means it goes from the machine shop directly to clad. The problem was that this gave a little bit more trouble for the welders because it was more tedious work, a little harder for them, because now they have a giant hole through where their bore is. So this manufacturing process was more efficient in workflow and scheduling, but in the clad shops it gave them some troubles. So you can imagine this picture here with the hole. The cladding operations would have to manually start and stop the process, the welding process, as it reached these intersections. Cladding operators would spend hours leaning over the part. They'd stop the weld at just the right spot, and then they'd manually rotate to the starting part. They'd use a push button or joysticks to do this, and then restarted the cladding process over and over until the top of the hole is reached. Many times the part required rework because the operator stopped too early, or they tried to weld through the hole, which doesn't work very well. So this created a need for automatic intersecting bore software to start and stop the arc as it came to this intersecting bore crossing area. It double-clicked. So of course this did require a little more complex formula than 2 pi r, but the trick was to make it simple to teach on the shop floor. We needed 5 dimensions to calculate this intersecting angles. The first was the vertical start position of the weld, the start of the hole, the end of the hole, the end of the weld, and the diameter of the main bore. Because of the constant surface speed software, we already knew what the main bore diameter was. So what we did is have a simple process for the operator to jog the torch to these 4 other areas and to teach the vertical position of those areas, and then we could use that information, throw it in some trig formulas, and calculate these start and stop points. That was the creation of the ARC-V. We don't know what happened to 2, 3, and 4. We won't talk about those. So as cladded parts continued to increase in complexity, we found that they were no longer conducive to rotating tables. Many non-circular shapes created a need for the part to remain stationary and for the torch to move around it. The most flexible way to perform this motion is with a machine capable of complex kinematic motion. Many of you will be asking, what does kinematic motion mean? Well, in robotics, kinematic is basically geometry in motion. It's having a known speed and location and then using geometry of the system to calculate any unknown position. All articulated arm robots will use this, and multiple axis CNC machines will use kinematics to position the tool. So for example, if we want to move the tip of a welding torch from point A to point B, we start by calculating the new target position and then use the geometry of the machine, like the axis links, the rotation angles, to calculate the individual servo motors positions in order to make that move into some point in space. The trick of it, though, is that all these calculations are executed 1,000 times a second, so you have nice fluid welding motion. Our first rotating head cladding system utilized a CNC-based manipulator. So it had X and Y and a Z cross slides, with they're pretty large, with a rotating head. We used G-code so the operator could completely customize the motion control, but this added complexity in creating the programs because it was G-code. The controller was a CNC-based system, so it handled all the kinematic motion, and there's standard kinematic formulas for this XY motion. So as the torch rotated, the controller calculated the movements and created a circular motion similar like a cutting table, you see, like a plasma cutting table. So with these X and Y motion now, we had the ability to do circles and linear moves, or straight welds. As the complex parts become more common, we believed a simpler operating machine was necessary. What we did was combine the easy-to-use ARC-V teach and repeat programming for the intersected bores and for the complex part configurations, and we combined that with the ARC-6G's CNC kinematic motion. We decided to build the machine with a 360-degree base and a boom axis with the rotary head. So out of those 3 motions, we had to develop the kinematic formulas because it's not a standard type of kinematic machine. So what we did was, based on the torch rotation, we calculated the positions of the boom and rotary base and interpolated the circle by moving the rotation base, extending the boom, and then as it came around, we retracted the boom and the base would go the other direction to kind of make that motion all fluid. For linear moves, we had to do just the opposite. We locked the rotation of the torch would have to change as you're moving in the X or Y distance, and so all 4 of those motors were moving at the same time and coordinated to make the movements that was desired. So after the rotary head systems were pretty well developed, we went into the lab, and our customers were challenged to make the cladding process more efficient, and so do more with less. So we went to the technical service lab, which that's this area here, and we wanted to find out how fast we could push single wire cladding. We wanted to keep a single wire. We've tried 2 wires and that kind of stuff, but anytime you add 2 wires, you add the cost of a wire feeder, hot wire power supply, and more importantly, the difficulty of getting 2 wires into the welding puddle. So we basically use the same 045 Inconel wire that's commonly used. We increased the travel speed, wire speed, welding amps, hot wire amps, and the pulse rate. Sounds simple, but what we had to do is develop some software to ramp this all up, because you can't just start at these higher speeds. You have to work your way up into these speeds after some heat gets into the part and the process gets fluid. We also had to mechanically design the machine to rotate the parts at a higher rate than previous other machine designs. All the cladding systems built today have this high deposition software. We can rotate about up to 8 pounds per hour, or we can weld at 8 pounds per hour. In that video, you've seen the high rotation speeds, the fast wire speeds. So that's trying to get as much clad material into the part as possible. I believe Dave's got some samples set up you'll see on a tour as well. So as we continued to push the cladding system technology, we saw a shift in capital project requests. They kind of went away from purpose-built machines to a more flexible manufacturing system. This machine here is what we call the ARC-V Infinity. It's much like the ARC-V-I system, where it has the same controls, the same HMI, the same feel, the same programming techniques, but it's based on a robot. Our motion control software continuously streams move commands, X, Y, and Z, as well as torch rotations, or yaw, pitch, and roll. The rotation head is an axis on its own. So we have to coordinate this same linear and rotation motion as you see in the other rotating head cladding systems. So in effect, this is a 7-axis robot. It has redundant safety monitoring. So what it's doing, it's limiting the speed of the robot to a safe speed. And it also has work cell restrictions where the tool can't go past certain areas. So by replacing the column and boom manipulator with a robot, we now have a major component of the machine that's a general purpose automation device, where the column and boom system kind of has one purpose. The robot tooling, which is in this case the rotary head that we designed, can be removed and, if needed to, changed out to something else at a later date and provide other forms of automation as production cycles fluctuate. Other advantages of this new robot cladding design is the ability to orient the axis of the torch rotation at angles other than vertical. So in this picture here, you see vertical like all the other historic cladding machines we've built operate pretty much. But with the robot, we can tilt it at an angle and even go horizontal. So this means is like large multi-port valves that would typically require a tilt and rotate positioner to position or reorient these bores vertical is no longer necessary. So this can eliminate the part positioner, which could save up to hundreds of thousands of dollars. They're big, very expensive positioners. It also can save time for bolting the parts up to the positioner, aligning it, moving it around. So that's a couple of the things that we're looking at. We're just starting into this. We've released it in November. We actually have a unit here to take a look at when you guys go on your tour. Yeah, so I want to thank everybody for listening to me, and appreciate y'all coming out. And with everybody here in the room, we can continue advancing not only cladding, but the other segments of industry that we're working on.